Okay, so let's talk about Chapter 4, which is applications of derivatives. So yeah, it's what it sounds like. It's all kinds of things you can do with derivatives. Um, One of them is to find the absolute maximum and minimum values of a function over an interval. The first example we do is going to be like that. So you just have a function and you have an interval, and it says find the absolute extrema or find the absolute max and min values. And this is an example of an application of derivatives because you use derivatives to solve this. Of course, we're going to find the derivative and see where it's undefined and see where it's zero, and those give us our critical numbers. And, well, we'll get into that later. But the work we have to do involves taking derivatives and then solving equations. Then there's questions that are about, you'll have a function, and then I'll ask you something like find the intervals where it's increasing or the intervals where it's decreasing, and identify any local maximums or minimums. And then I almost forgot to put this, so this is the next star down here, is concavity. So I would ask you the same questions about concavity, like what are the intervals where it's concave up, what are the intervals where it's concave down, and then to identify any inflection points. And of course, these two things kind of go together, but this stuff, the increasing, decreasing, local max, local min stuff, that's all first derivative questions. That's just like you don't need to know anything about the second derivative to answer these questions. The concavity and inflection points is very similar, except you're talking about the second derivative. But we'll get to that. Then there's L'Hopital's rule, which is limits, and you'll find we already sort of practiced L'Hopital's rule a couple days ago when we were talking about Chapter 2. Of course, we didn't know L'Hopital's rule at the time, but now that we know L'Hopital's rule, we can use L'Hopital's rule to do many of the limits from Chapter 2. But I'll do some more examples using L'Hopital's rule this time. I just want to remind you. Then there was also optimization problems. These are like word problems where often you are trying to maximize the volume or minimize the surface area or something like that of some shape. And then we have antiderivatives. So these are the main things that I would ask you on the final exam out of Chapter 4. We covered more things out of Chapter 4, but I'm kind of trying to give you the main topics that I'm going to ask you questions from on the final, which is not all of them. For example, I'm not going to ask you about Newton's method on the final. We did a quiz on Newton's method and some homework on Newton's method, but I'm not going to ask you about Newton's method on the final. Anyway, let's go through some examples. So like I said, the first one is finding an absolute maximum and minimum values for this function over this interval. So how do we do this? We start by taking a derivative. Here I have the product rule. So the derivative of x is 1. The derivative of this, I don't do the derivative of this. I just leave this alone. And I'm gonna write the 1/2 power instead of the square root. I left it alone, but I just wrote it in a different way. Plus x times the derivative of this. This is, of course, a 1/2 power, so its derivative looks something like this. So the inside is 1 minus x, and then before I forget, I have to multiply by the derivative of the inside, which is -1. Right? Okay, so that's the derivative. And what do we do with this? First, we have to say where it's undefined. And this one, of course, it's very easy to forget to check where it's undefined. This one may be undefined because I see a negative power, and we're going to have trouble if I try to do 0 to a negative power. So this is undefined if I have 0 to a negative power. In other words, if x equals 1, then f prime of x is undefined. But that's really the only, that's the only negative power that I see, and I don't see anything else that would cause this to be undefined. So that's it. I should also check where this is 0. So yeah, I'll just rewrite this, I guess. And maybe I'll simplify it too. So this is like minus 1/2 x. 1 minus x to the minus 1/2. And that we're setting equal to 0. So now we have to solve an equation. I think it would be smart if, yeah, I don't like, as I'm solving this equation, I don't like this negative power. I'm going to multiply both sides. Actually, let me just rewrite this real quick because yeah, I'm multiplying both sides by 1 minus x to the 1/2, because if I do that, that will cancel with this. Of course, I have to distribute it. I have to take this and distribute it here and here. But when I'm distributing it here, it'll just cancel. The positive power and the negative power just cancel. And of course, I have to multiply this on the other side too. Of course, the other side doesn't really care what I multiply it by because the other side is 0, so I'm always just going to get 0. So that side is 0. Let me carry through this multiplication. So these powers are going to add, because when I multiply 1 minus x to this power times 1 minus x to this power, I add the powers. So that would be to the 1 now. And then, well, the same thing happens here. Like earlier I said that it canceled, which it does because you add the powers, and if I do a half plus negative a half, I get 0, which is like, something to the 0 power is like 1. In other words, that's essentially like they cancel. There's nothing left. It's just 1. Great. So this is a lot simpler. So this is actually just 1 minus x minus a half x equals 0. So yeah, let me make this short, or try to. I would move this over. This makes 3/2 x, of course. So x equals 2/3. Okay, now, yeah, hopefully I have enough room for this, but where am I now? I took the derivative, I found where it was undefined, I found where it was 0, and now, because of the type of problem this is, all I have to do is plug in the critical numbers and the endpoints. You plug them into the original function, f of x, not the derivative. So I have to find f of 1. I have to find f of 2/3. I have to find f of -1 because it's an endpoint. And I would have to find f of 1, but actually I'm already finding f of 1. So this is a funny, there's a little coincidence that's happening here, if you notice. 1 was one of our endpoints, so we would definitely have to find f of 1 anyway. But as it turned out, when we were taking the derivative and figuring out where it's undefined, we also found that it's undefined at 1. So, but that's okay. We'll just find f of 1 once. There's no reason to find f of 1 again. So it's really just I have to do these 3 things, and whichever one is biggest will tell me the absolute max, and the smallest will tell me the absolute min. So, okay, f of 1, I can plug that in here. That's easy because I see that I'm going to get the square root of 0, which is 0. So this just gives me 0. F of 2/3. Okay, that's not very nice, but it's going to be 2/3 times the square root of 1/3, right? And I can make this look nice if I want. This is like 2, because the square root of a fraction, you can just do the square root of the top and the square root of the bottom. So this is like 2 times the square root of 1 is just 2. 3 times the square root of 3 is that. And I could even rationalize the denominator, but by now you know that I don't really care much for rationalizing denominators. And just because, well, okay, let's see. Hold that thought. Let me move on. I want to find f of -1 next, because I'm going to plug that in, and I'm going to get -1 times the square root of 2, because this would be 1 plus 1. So that's -√2. And okay, so let me go back to a second ago when what I was about to say is let's plug this in a calculator to find a decimal. Because this isn't a nice number. I can't really tell you how big this number is. And as I do this, in the end, I'm just comparing these 3 numbers, and I need to know which one's biggest and which one's smallest. So usually, if I have numbers that aren't very nice, I just plug them in a calculator to get a decimal. And all I'm doing when I do that is I'm just checking which number is bigger than the other one. In this case, actually, I can tell. Just because this one's positive and this one's negative and this one's 0, it's clear that this one is the largest and this one is the smallest, just because it's positive and it's negative. So I'm not going to bother with a calculator. So, right, I have just enough room to draw a proper conclusion. We have an absolute max of this one at x equals 2/3. We have an absolute min of this one at x equals -1. And that's my answer. Okay. So let's do one where you have a function and you have to talk about where it's increasing, decreasing, local max, local min. And then part 2 is you do the second derivative stuff, where you're doing intervals of concavity, concave up, concave down, and then determining inflection points. So part A is all about the first derivative. I'm not even going to find the second derivative for part A. This derivative would be 1 plus, okay, now I've got chain rule, right? The outside function is the natural log, and the derivative of the natural log gives you 1 over the inside. And then for the chain rule, I have to multiply by the derivative of the inside, like that. Right? So I don't like to simplify unless I have to, but we're going to work with this, so I'm going to simplify it. And right, so what I'm shooting for here, what I would like to produce is one of these number lines for f prime of x. I'm going to draw a number line. I'm going to mark certain points on the number line, and that's going to break the number line up, and then I'm going to fill in each piece with a plus or a minus, and the pluses are going to tell me where it's increasing, and the minuses are going to tell me where it's decreasing. And the transitions between pluses and minuses will tell us where there's a local max and a local min. And to make one of those number lines, I need to determine the critical points, which is where the derivative is 0 or undefined. So here I go. I'm looking at this, and the first question I always ask, because if you don't do this first, you're likely to forget, I ask where it's undefined. This one, maybe I do see a little danger that this would be undefined, because I do see division here. So I would be in trouble if this bottom was 0. But once we think about it, we're going to see that never happens. I mean, we can solve this. And right here, I see I'm about to do the square root of a -1, so there's no solution. So we saw a little bit of danger, but then we checked, and then we found that this is actually never undefined. The other thing we should do is set it equal to 0. So I'm setting this equal to 0. And yeah, what should I do here? I don't really like, if I'm solving an equation, one thing I like to do is to just get rid of fractions. I don't like fractions. So I'm going to multiply both sides by something to kill the fractions. I'm going to multiply both sides by that. And of course I have to distribute, so when I take this times 1, I just get 1 plus x squared. And when I take this times this, I get 2x. And of course 0 times anything is 0. So this tells me x squared plus 2x plus 1 equals 0. This is nice because I can factor it. This is x plus 1, right? So x equals -1. I am ready for this. Because I found all my critical points. The critical points are the numbers that I'm going to mark on the line. There were no spots where this was undefined, and then there was only one spot where the derivative was 0, so this isn't that complicated. I just have one mark. And so now this is going to have a plus or a minus, and this is going to have a plus or a minus, just depending on whether the derivative is positive or negative there. And yeah, so sometimes you can just sort of look at the function and like figure out whether it's going to be positive or negative, but somehow maybe I'm having trouble here. But that's okay, I can just plug in numbers. Why don't I plug in -2, just because -2 is a number that's on this side. And that would be 1 plus -4 over 5. So 1 minus 4/5 would be 1/5. And that's positive. What about over here? I always like to plug in 0 if I can, because it's always easy. F prime of 0 would be 1 plus, and this is where it gets easy, 0. So that's also positive. So actually, and this is a little bit of a funny thing to happen. It's not that strange, but usually it just goes plus minus, but we do often, it's not uncommon to see two pluses in a row, and that's what we're seeing here. So I would say, let's draw our conclusion for part A. And yeah, so maybe now is a good time for me to give a little speech about this. So this is increasing from negative infinity to negative 1, and then it's also increasing from negative 1 to infinity. And a common question is, should I lump these intervals together and just say that it's increasing all the way through? I don't plan to be too picky about that issue when I'm grading, to be honest. When I'm grading, I would accept either way for this one. And one reason I'm saying that, and this is important, is that this original function is continuous at x equals negative 1. Like the original function, it's okay to plug in x equals negative 1. Like, it doesn't cause you to do the natural log of anything that isn't allowed. You can plug in x equals negative 1. So this is fine. And if that's the case, if the original function doesn't have a domain restriction, then you can lump these intervals together. What we're just checking for is that there isn't anything crazy happening here, like a vertical asymptote or anything that would cause the function to be undefined. And as long as it's defined the whole way through, when it's an elementary function, it's continuous. If you have two intervals where it's increasing in a row, you can just lump those together. So here's an answer that I would accept. Like I said, you don't have to lump these intervals together as far as I'm concerned. But if you would like to, I would also accept this answer. I would accept this answer, or I would accept this answer. So that's where it's increasing. Where is it decreasing? Nowhere. Do we find any local maxes or mins? Well, no. A local max would be if I saw a plus followed by a minus. A local min would be a minus followed by a plus, and we didn't see any of that. Okay. Let's talk about, and do I have, sorry, I need more paper, I think. Just 1 second. All right. Because I need to do part B. So, okay, just to recall, this was a two-part question. We started with this function. Part A was a bunch of first derivative stuff. Part B is finding intervals of concavity and inflection points. So here's what I'm going to do. I already found the first derivative, and for part B, I am being asked questions about the second derivative. So I'm going to look, since I already did the first derivative, I'll just do the derivative again. When I do the derivative of this, the 1 disappears, and I'll do the quotient rule to this. So it's bottom times derivative of the top. Oops. 1 plus x squared times 2 minus the top times the derivative of the bottom, which would be 2x times 2x over the bottom squared. Okay, So that's the second derivative, and I am going to clean it up. So this is 2 plus 2x squared minus 4x squared over, and on the bottom, I think I would prefer to keep this factored, actually. I mean, I could try to square it out, but for what I'm going to need to do, I think I'm better off if I just leave it as it is. And there's like terms on top, so I see a 2 minus 2x squared. Right? Okay, so I took the second derivative, I cleaned it up, and now I'm going to run through the same procedure that I just did to the first derivative. So I have to check where it's undefined, and then I have to check where it's 0, and then I have to make a number line where I mark those points, and in the in-between areas, I have to fill in each one with a plus or a minus. And since I'm doing the second derivative, the pluses are going to be concave up, the minuses are going to be concave down. And wherever I see a plus change to a minus or a minus change to a plus, that's going to be an inflection point. So that's what I'm about to do. So check where this is undefined. It is a fraction, so it would be undefined if this bottom were 0. Of course, I'm having a little bit of deja vu here because once I write this down, I think about solving this equation. The first thing I would do is the square root to get rid of this square. So that would tell me 1 plus x squared equals 0, and then x squared equals -1. And now I would be about to do imaginary numbers, so I just say no solution. Okay, so this, as it turns out, it's never undefined. We should set it equal to 0. So I set it equal to 0. I'm going to multiply both sides by the bottom. Like this. This cancels this. 0 times anything is 0. So I get 2 minus 2x squared equals 0. Let me sort of put arrows just indicating what order I went in here. So I got here, and then this brings me here. 2 equals 2x squared. X squared equals 1. X equals plus or minus 1. Okay. So where am I? I am trying to make my number line. I checked to see where this function is undefined, and I didn't find anything. And then I set equal to 0, and I found these. These are the numbers that go on my number line. And now I fill in pluses and minuses accordingly. So yeah, how about I do f double prime of -2, because that's a number that falls in here. And I'll just plug it in. I don't like looking at this. It's not that easy for me to tell what's going on. So I'll just plug it in and see what happens. So I get 2 minus 2 times 4, so 2 minus 8 over 1 plus 4, so 5 squared. And I can see this is going to be a negative number. The top's a negative number, the bottom's a positive number, and I don't care about this that much. I just care about whether it's positive or negative, so at this point I'm just going to fill in a minus. For this one, let's plug in 0 because we can. This should be easy. I'm going to get just 2 on the top and just 1 on the bottom. So that's positive. And then over here, why don't we do f double prime of 2? And actually, f double prime of 2, I think that's going to be the same as plugging in negative 2, right? Because I get 2 minus 2 times 4, so it's 2 minus 8 over 1 plus 4 squared, so 5 squared. And sure enough, this is the same thing I was getting. This is a negative number again. All right, so concave down, concave up, concave down. Inflection point, inflection point, because this is an inflection point because I have opposite signs on both sides, and same reason here. For an inflection point, it doesn't matter if it's a minus on the left and a plus on the right, or if it's the other way around. We call them all inflection points. So typically, to talk about an inflection point, you would talk about the point on the original function I know the x-coordinate of an inflection point is -1, and then I'll figure out the y-coordinate. And I know the x-coordinate of another inflection point is +1, and then I'll figure out the y-coordinate. I'll just do that underneath. So f of -1 is, oh geez, what's the, yeah. The original function is this, so f of -1 would be -1 plus the natural log of 1 plus 1 is 2. So that goes here. And then f of 1, whatever it is, will go here. And f of 1 is 1 plus natural log of 2. So there we go. That's all it wanted. It just wanted the intervals of concavity, and it wanted inflection points. So there they all are. And yeah, I was going to do several more examples in this video, but it is maybe getting a little bit long. So let me cut this one off and start a new one.